So it is my greatest pleasure to welcome you all here today for the first lecture of, Introduction to Computing and Programming, also known as CS50 or, CP CS100 officially here at Yale. We couldn't be more excited to welcome you all here. My name is Patrick Rabeschini. I'm the head instructor for the class. I am here representing a group of about 60 staff members who will work with you throughout the semester. This number is almost 60 of us, yet alone the extraordinary level of commitments that we put into this class makes CS50 the class at Yale University that offers the greatest level of support to all of you. And we couldn't be more proud of offering this class here again. In fact, as you will soon experience, CS50 is much more than a class. It's a community. And you will be part soon of this community. This is the second year that Yale is offering this class. We are building on the extreme success of last year, where for the first time here at this university, undergraduate learning assistants were adopted in classrooms. It all started with this class last year. So as you know, the class is taught jointly with Harvard University to teach this course. We can count on the great expertise of David Mullen and the Harvard team. So David has been teaching CS50 for, 10 years now. And every year he has been pushing the boundaries and improving the classroom experience. Again, we couldn't be more happy to continue this collaboration with them. In fact, one of the most interesting parts, I will say, of running this class now, both at Harvard and here at Yale, is the really incredible cross-fertilization of ideas aimed at improving the learning experience to you all. So as a result of this extensive collaboration between the two universities, CS50 is proud to announce the new version this year with noticeable changes. David will all tell us about them now. So please, this being said, please join me and to give a big round of applause to welcome David and the Harvard team here at Yale.
Thank you. This is CS50, Harvard University's and Yale University's Introduction to the Intellectual Enterprises of Computer Science and the Art of Programming. And what that means is that this course ultimately is about problem solving. Indeed, many of you might have come out of high school or have spent the past couple of years wondering what some of your friends did last year or in other classes. And yet, the reality is, no matter what we do at the end of the day in this class, it's going to be about problem solving. And as such, perhaps take some reassurance in the fact that 73% of the students that take this class, both here at Yale as well as at Harvard, have never taken a CS class before. So if you're sitting here in the audience today wondering why you are sitting here in the audience today, or maybe you just followed along with some friends, or maybe you've been a little curious as to what computer science and in turn programming is, realize that most of your classmates to the left and to the right of you are very much in that same demographic. And indeed, if we look at last year's statistics, within the student body of CS50, both here and at Harvard, 58% of students describe themselves as less comfortable, 9% is more comfortable, and then 33% somewhere in between. And there's no formal definition of what these buckets means. You sort of know you're less comfortable if you are. You're feeling a little uneasy with maybe being in the class. You're not quite sure if a computer science class is ultimately for you, and realize that you are in very good company. And indeed, the grading and the assessment and the feedback and all of that support structure in the class is ultimately very much individualized, more so than most any other class by design. And indeed, what ultimately matters in this class is not so much where you end up relative to others, but where you, in week 11, are last, and relative to yourself in week 0, here, our first. So what does that mean? Well, this means that of those 73% of students last year that had never taken a CS class before, by the start of the semester, they were dabbling in a language called Scratch, which we ourselves will see here today. And by the end of the semester, had they gone through this entire list of challenges, starting with a language called C, implementing what's at first glance going to be a bit of a challenge for some, but fairly gratifying once you get Super Mario bouncing up and down a pyramid implemented, albeit with just something called ASCII art. Implementing last year, what the students last year then did after that was implement their own Caesar cipher and Vigenère cipher, so encryption algorithms with which you could scramble information and then unscramble information to send secret messages. The game of 15, if you remember from childhood or some party favor, that little plastic game where you move the numbers up, down, left, and right to try to get them in order, actually implementing that game and solving the logic required there. And then we dabbled in forensics last year. So by mid-semester, students who had never used their keyboards for this purpose before were writing software to recover, so to speak, JPEGs or photographs that we had accidentally deleted from a digital memory card from a camera, recovering secret messages from inside of a bitmap image and other such types of graphics as well. We then transitioned to giving the whole class a dictionary, just a really big text file with 150,000 English words, and everyone was challenged to somehow read, so to speak, those words into memory, into the computer's memory, and then answer questions of the form, is this a word, is this a word, is this a word, really just implementing a spell checker, and then challenging each other with a big board, a leaderboard, to see who could use the least amount of memory and the least amount of time to actually spell check large documents. We transitioned from then to implementing one's own web server. So not making web pages in languages like HTML and CSS, if you're familiar, but actually implementing the server that listens on the internet for requests from browsers and then responding to those requests. Then implementing our own E-Trade-like website where students could buy and sell stocks, drawing in nearly real-time stock quotes from Yahoo Finance and allowing students to see how their portfolio develops. And then finally, a mashup of Google News and Google Maps, whereby students by term's end had the ability to click and round and search on a Google map and then see all of the news articles that are proximal to those particular areas. So truly going from 0 to 60, and along the way having what we had last year called hacker editions that raised the bar further for those of you who might very well have a good amount of experience, being in that 9% of more comfortable. So realize that there's a very high ceiling even within those challenges for students coming from a different background. Because at the end of the day, we're ultimately focused quite simply on this. But what does this mean, problem solving? So let's propose that we distill it like this. So problem solving is really just this kind of picture. So you've got inputs to some problem, something you actually want to solve. The goal is to get outputs, a solution to that problem. And then in the middle is what we'll call a black box. You don't necessarily know or even care what's inside that black box. All you know is that when you feed input into it, you hopefully get output or a solution from it. And while today we'll look both at inputs and outputs, we'll long-term and over the course of the whole semester focus on what's inside that box, and therein will lie something called algorithms, step-by-step instructions for actually solving some problems. But what's an example of some input? So maybe a simple thing at the start of every school year, someone might want to take attendance. So we might do 1, 2, 3, 4, 5, 6, and how might I keep track of that information? I might just go 1, 2, 3, 4, 5, 6, and just use sort of single digits, or I could actually, record this a little longer term. And how do I represent all the humans in this room? Well, I might do something like, okay, I see one person, all right, I see another person, a third person, and so forth. But no one counts people like this so literally. Most of us, if we're even going to draw anything at all, are probably going to go 1, 2, 3, 4, maybe get a little fancy, 5, 6, 7, 8, 9, 10, and so forth. And that's actually a system called unary. Uno, like uno, implying one, where you just have one letter of the alphabet. You just got this hash mark. And I, for efficiency, just drew these hash marks ultimately as straight lines, but I could have drawn them as little stick figures, where to represent one person, one input, I just draw a stick figure or a hash mark. But this isn't all that expressive. If all I have is these hash marks, let alone stick figures, how might I represent something like the number 15 or 15 people in the room? I might have to do something like 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. And it just does not scale very well. As the inputs get large, we need a better system than this. And it turns out that the system that computers use is not all that different from what you and I know. In fact, most people in this room, even if you are among those less comfortable, don't necessarily know how your Mac or PC really works, you've probably at least heard that underneath the hood are zeros and ones, the so-called binary system. So indeed, computers have more than just hash marks in their vocabulary, but not as much of a vocabulary as we humans. Indeed, we humans don't use binary, bi meaning 2, 0 and 1, but decimal, dec meaning 10, 0 through 9. So we have a lot more expressive capabilities in our normal human world, but I'd argue that these systems, binary and decimal and everything in between and beyond, are actually all quite familiar. For instance, consider this example here. 123. So this really is, of course, a number we know as 123. But all I just drew was just this pattern of symbols, glyphs, so to speak, sort of shapes on the board in chalk. But why do we immediately intuitively grasp this as 123? Well, if you're like me in grade school, you probably learned that this is this is the ones column, this is the tens column, this is the hundreds columns. And why is that useful? Well, the simple arithmetic you now do to get from a pattern of symbols to a number we understand intuitively is what? 100 times 1, and then 10 times 2, and then 1 times 3, which of course is just 100, and this is 20, and this is 3. And so if we add those together, so therein lies the sort of reasoning behind why this set of symbols means something real and numeric. Well, computers do the exact same thing, but they only can count as high as 1, whereas I was able to count as high as 3. And in fact, if I kept going, I could go as high as 9 in this system. Computers only have zeros and ones in their alphabet. So what does that mean? Well, it just means that if a computer wants to represent, say, the number 0, maybe using 3 characters, 3 letters of the alphabet, so to speak, that's how a computer represents 0. So not all that scary so far. It's exactly what we humans would do. And in fact, most of us would just ignore the leading zeros anyway. A computer, if it wants to store the number 1, turns out is going to do this. And a computer to store the number 2 is not going to do the unary system, which I alluded to earlier. It's actually going to do this. And this is probably where the pattern starts to become less obvious for most folks. That's 2. This is 3. Curiously, this is now 4. And now it really does seem to be perhaps cryptic, but it's not if we consider what binary really means. It means you have 2 letters of your alphabet, so two possible characters for each placeholder. So that really means we're going to need a 1's place, a 2's place, a 4's place, and then 8th and 16, 32, and 64. And what's the difference there? Like these are 1, 2, 4, 8, 16, 32, 64. And before we had 1, 10, 100, 1,000, 10,000. What's the similarity there? What's the pattern? Yeah. Yeah, powers of 2 instead of powers of 10. And so if I wanted to keep going, 8, 16s, and so forth. But now, if you have this sort of clue, now the binary system is actually pretty straightforward. Why is this pattern of zeros in the world of computers 0? Well, because it's 4 times 0, 2 times 0, 1 times 0, and you get 0. Why is this the number 1? Same reasoning, but now we have a 1 in the 1 column. Why is this 2? We have a 1 in the 2's column. And how then do I represent, say, the number 7 in binary? Say louder. 3 1s. So 1, 1, 1, because we just need 4 plus 2 plus 1 gives me 7. All right, so from there, how do we represent 8 with 3 placeholders? Yeah. Yeah, 1, 0, 0, 0. And yet, maybe I kind of technically need to add another placeholder to the board. If I want to fit that, I indeed need to do something like this. So I actually need to use now the 8's column. And that's fine. But the curious thing in computing is that that's going to cost us something. You need more RAM in your computer now. You need more memory because you need something physical to store that additional bit, so to speak, binary digit. And indeed, all that's happened here, like the decimal system, if we keep adding numbers up and up and up, we go to 5 to 6 to 7 to 8, it's like carrying the 1, literally. And then everything else goes back down to 0. But how do we actually represent these things physically in a computer? Well, at the end of the day, the only physical input going into my computer here is this like power cord, so electricity or electrons from the wall. And so how do I get from something physical like that to actually representing an idea like this instead? Well, what could we do? We could consider that, all right, maybe if electricity is flowing, I could store it and hold on to it. And if I'm holding on to some electricity, that's just going to arbitrarily represent a 1. And if I pull the plug and there's nothing there, that's just going to arbitrarily represent a 0. So if something's there, 1. If nothing's there, 0. Or you can make this a little more visual. Here is a 0. There's nothing interesting going on about the back of my phone. But if I allow a little bit of electricity to flow, even though it's a little bright in here, my flashlight went on. So I'm storing a charge, and ergo, this phone now represents a 1. So 0, 1. So with one iPhone, how high can I count using this kind of approach? I mean, to 1, it's not all that compelling. So what more could we do? Well, let's see. Is anyone on their phone right now that I could borrow? Anyone who has a phone with a flashlight built in? May I borrow? I don't need it unlocked. All right, thank you. Let me borrow this. All right, so if I now scroll up and here, what am I representing now? Yeah, so it's a 3 because this is in the ones column, this is in the twos column, so 1 plus 2 is 3. And then if we try to get really creative, oh, thank you, very preemptive. All right, and now have 3 iPhones, all right. All right, and now this, I won't do any further than this. What am I representing now? Just 7s. But I needed physically more memory in this case. But that's all it is. You can think of what's going on, thank you, inside of your phone as just being a switch that's being turned on and off. And if you've ever heard the word transistor, or if you've ever heard the marketing speak Intel inside, that's speaking to the kind of hardware that's inside of your computer. Intel makes CPUs, central processing units, which are like the brains inside of your computer. And these CPUs and things they're connected to have lots and lots of tiny switches, millions, billions of switches that can either be on or off. So computers, thankfully, like our Macs and PCs, can count way higher than 7 or 8 because they have way more than 3 or 4 bits, way more than the equivalent of the 3 flashlights that we just had. But now this starts to get pretty uninteresting quickly. If I now want to actually be able to do something more interesting, I want to be able to jump to something like this. So ASCII, it's not really a useful acronym, but American Standard Code for Information Interchange. It just means some years ago, we humans decided, you know what? We want to be able to do more with computers than just numbers. We don't want them to just be expensive calculators. We'd like to be able to do things like word processing, albeit very simply. Later, we had email and other such media. And so the world decided some years ago, according to this system, ASCII, you know what? In certain types of programs, anytime you see the equivalent of the number 65, like the pattern of bits, and we could do the math here on the board, the pattern of bits that represent 65, don't think of it as 65 in decimal. Think of it as arbitrarily, but globally consistently as the capital letter A. And then the world decided, you know what? Let's take another pattern of bits, and if we ever see the number 66, let's just assume that that is the capital letter B. Fast forward to H and I. If you see 72 or 73, that should be an H and an I, respectively. And so long as the whole world agrees upon this, so that when you receive an email or you get a file on a USB stick or something like that, when you see that pattern of bits, you know that it should be this letter or some other letter. But it's context specific, right? An email program might interpret these things as characters, but a graphing calculator or calculator might represent or interpret these things, of course, as letters. So with that said, quick little review. This is maybe a 3-character email that's been sent to me. Underneath the hood, it's all in 0s and 1s, but we don't care. We're going to start to abstract above the 0s and 1s to letters. And if I see a pattern of 0s and 1s that really represents 72, hint, hint, 73, and then 33, what's the message? So if you think back just a moment ago, hi was the message I was trying to communicate here, because H is 72, I is 73, and now 33, you wouldn't necessarily know this in advance, but it turns out if you actually see more of the chart and the system that humanity agreed upon years ago, it's just an exclamation point. And indeed, there is a pattern of symbols and numbers for every character that you might have on your keyboard. But all right, let's abstract further. If we don't want to just have things like numbers and letters, we actually want to implement graphics. Well, if you've ever heard the acronym RGB, it's kind of dated now, but it's still kind of there. RGB is red, green, blue. And it's just a system of saying, you know what? Let's use 3 sets of bits. A set of 8 bits, another set of 8 bits, and another set of 8 bits. And let's use those bits to store how much red we want on our screen, how much green we want on our screen, and how much blue we want on our screen. And this just means that if you have a big number for red, that means give me a lot of red. If you have a big number for green, give me a lot of green. And if you have just a little bit of blue, or a small number like 33, give me a little bit of blue. And if you happen to combine those 3 magnitudes, so to speak, you get this, you barely can see it on the projector here, but this like murky shade of yellow or brown. But this is to say, using that pattern of 8 plus 8 plus 8, that pattern of 24 bits, is how a computer would store that shade of yellow in one tiny dot or pixel on the screen. So we've gone from 0s and 1s to decimal numbers to letters of the alphabet, or more interestingly, colored dots. Well, what, of course, then comes next? Well, what is an image that you see on Facebook or get in an email or the like? Like, what is the definition technically of an image? Yeah? What is an image composed of, if you look really close at your screen? Yeah, it's just a whole bunch of pixels. In fact, if you take your laptop maybe later on and look really closely at it, depending on like how expensive the laptop is and how high quality the screen is, you might very well see all of the little dots on the screen. And those dots are each pixels, which means there's 24 bits representing every pixel in that photograph that you see on Facebook or that you just took on your iPhone recently. And so that's how we get to things like graphics. Well, what's a video? A video is just a set of graphics flying by the screen again and again and again. And so videos really are just patterns of bits representing grids, rows and columns of dots flying by the screen, image after image after image, aka motion pictures. So that's it for inputs and outputs. All we have now is an assumption that, you know what, if we want a computer to represent information, we have a system for doing it. We can do it with zeros and ones at the end of the day, but we can abstract, so to speak, on top of that so as to represent more interesting things. And here on out in CS50 and in computer science more generally, we now stand on the shoulders of all the people who came before us who figured that out, and now just assume that computers can represent inputs and outputs. But now let's actually do something with them. So an algorithm is just a set of instructions, step by step, for solving some problem. And what might one such problem be? So this is an old school technology, a phone book. And inside of a phone book is a whole bunch of names and numbers. And those names are generally sorted alphabetically. So if I wanted to find someone in this phone book, like Mike Smith, what's a typical human going to do? Well, you could simply open it up, look at the first page. I don't see Mike Smith. Turn to the second page. I don't see Mike Smith. And just keep going and going.